Welcome back to part 3 of Kinematics. And we're still working our way through vorticity. We had talked about Earth's vorticity in the previous video. Now we're going to look at relative vorticity. And by definition, relative vorticity is the vorticity that results from the air itself, the spin of the air. We use the symbol, the Greek symbol zeta, to represent the relative vorticity. There are two things that determine the spin of the air, and those two things are the curvature, how the air curves, and then secondly, if there's any shear in the atmosphere, wind shear. Now we're looking at horizontal, we're looking at a weather map, so we're talking about horizontal wind shear and horizontal curving. So we're going to look at this two different ways. One way is natural coordinates, that's easier to understand. Cartesian coordinates are a little bit more difficult, mathematically a little bit difficult. So let's do the easy way first. We'll do S and N coordinates. So here we have flow going around a curve, and remember the S coordinate is always in the direction of the wind, that's the streamline, and the N is normal or to the left, 90 degrees to the left of the wind. So we're going to start out looking at two factors. Number one, the curve itself, how the curve affects it, and number two, the speed of the wind that's going through the curve. So first off, let's take a look at the curve. So here we have wind, you can see the V, and the V is the same. In other words, the wind speed is the same. But we have air flowing on the left around a big curve and air flowing around on the right a tighter curve. So you got a big curve and a tighter curve, big radius, small radius. Radius is the distance from the center out to where the wind is. And you can see the distance on the left is greater, the radius is greater, on the right it's less. So if the wind is going around at the same linear velocity, v, if it's 10 knots, then the angular velocity that is covered by the wind for the smaller radius is greater than for the bigger radius. In other words, the distance, the actual linear distance that the wind is traveling, let's say it's going 10 miles per hour, it's going to travel 10 miles across the smaller radius, but since the radius is much smaller, that's going to be a greater angular distance. And remember that vorticity is measured in terms of angles or degrees per hour per minute or per unit time. So vorticity is greater if there is a smaller radius than there is for a bigger radius. So vorticity, now we're talking relative vorticity, is inversely proportional to the radius of curvature. Small curvature, big vorticity. Big curvature, big radius, small vorticity. Okay, now we're going to change the speed and we're going to hold the radius of curvature constant. So in other words, we have the same circle, same radius, same distance from the center out to the, in this case, this ball. The ball is traveling at different speeds now. On the left, it's going slower. Maybe it's only going 5 miles per hour. On the right, it's going a lot faster. Maybe it's going 20. And it's pretty obvious to see that the one that's traveling faster is going to cover more degrees, the greater angular distance, than the one that's going slower on the left. So we say that faster wind speeds have greater vorticity and slower wind speeds have less vorticity. So let's put this together mathematically and summarize. It's proportional to speed, faster speed, greater vorticity, and it's inversely proportional to the radius of curvature. A tight spin means a faster vorticity, or more of a vorticity, greater angular vorticity. So here's our equation for curvature vorticity. It's the velocity divided by the radius, directly proportional to the velocity and inversely proportional to the radius. So C sub V here, we're talking C sub V is our curvature vorticity, directly proportional to the wind speed and inversely proportional to the radius of curvature. So that begs the question, when is it positive or negative? Because the wind can travel in different directions. It can rotate clockwise or counterclockwise. So as a reference, we have to come up with some way of describing when it's positive and negative. And we do that using natural coordinates. When we draw our natural coordinates, if n is pointing to the center, then we say it's positive. The radius is positive, and we have positive vorticity. If n is pointing outside of the center, when you draw your streamline, then we say that the vorticity is negative. So that's all we have for curvature vorticity. We're still talking relative vorticity, and relative vorticity is made up of curvature and shear. In the next video, we're going to talk about shear vorticity.